All right, we're on. So it's my pleasure to introduce Angus Wright, who is a research fellow in the German Center for Cosmological Lensing at the Ruhr University Bochum, at least my approximation of the pronunciation of that. He did his PhD at the University of Western Australia, where he studied the growth and evolution of baryonic mass as a member of the Galaxy and Mass Assembly collaboration. After that, he worked for the Kilodegree Survey at the Argelander Institute for Astronomy at Bonn University, studying weak gravitational lensing. Lately, his research has been focused on weak lensing survey science, particularly optimizing photometric image reduction and analysis methods, systematics mitigation, and statistical analyses. Beyond weak lensing, Angus is a keen astrostatistician and also describes himself as a passable astronomy outreach presenter and an enthusiastic but nonetheless mediocre golfer. So with that, I'll hand the floor to Angus.
Thanks very much, Stephen. I wasn't sure if my golfing prowess was going to make it onto the recording, and I'm very glad it has, because I can tell you that it has not improved over the last year. Uh, so thank you very much for having me, everybody. I'm very happy to be here, even in the virtual format. As you may or may not be aware, I was supposed to be giving this seminar back in March. Or a seminar very much along these lines, but I was the first one who was cut down by the pandemic in terms of the talks that we gave here. So I'm glad that I've managed to come back towards the end of the year and sort of bring 2020 to a close somewhat, with sort of completing the circle here. So as Stephen said, I'm going to be talking about cosmic shear in 2020. And my plan was originally to give you guys basically a summary of all of the developments that had happened in cosmic shear in 2020. And after about 10 minutes of exploration into that particular topic, it became very, very apparent that I had bitten off far more than I could possibly chew. And instead, I decided to sort of focus a little bit more on what is directly in my wheelhouse. And unfortunately, it's come off a little bit more kids-oriented than I initially intended. So my apologies to my fellow cosmic shear people, particularly those of you working within LSST and Euclid, because there is far less of your work in here, which is probably should be than I have. But so my apologies. To start off, I just wanted to, because I'm not entirely sure of what the background of everyone watching is, I'm just going to give a very quick overview or introduction into gravitational lensing. And so those of you, many of you may be aware, so gravitational lensing is just very roughly the imprint or the distortion that happens on background images of objects due to the presence of a gravitational potential in the foreground. So what you can see in this very, very cartoony picture is a background galaxy shown here in the purple. And you can see two light rays coming from that particular galaxy, which have been passed through a gravitational potential here in the form of a foreground galaxy cluster. And you end up with these orange deflected light rays that end up intersecting at the Earth, so being visible by us. Now, if we make this slightly less cartoony, then you essentially see this. What happens is you have this image, which is what we would see on sky, shown on the right here, where you have the foreground image of the galaxy cluster, and then you have lensed images of background galaxies shown here as these arcs that you can see, these orange arcs on the top and the bottom. And that's the sort of thing that this gravitational lensing signature imparts on a galaxy image, which would, in the absence of gravitational lensing, appear like this image here at the very back. And if we can go one step further into the less cartoony stakes and actually look at an image of gravitational lensing in the strong lensing regime around a galaxy cluster, and that's exactly what you're seeing here. So we have a picture of a galaxy cluster, and you can see all these beautiful arcs and all this coherent distortion of galaxy images that sort of radiate radially outwards from the center of the cluster. And that's essentially the gravitational lensing signature that we're interested in. And so here again is just a noiseless simulation of gravitational lensing, which is nice because it shows both the strong lensing regime, which is basically down here in the bottom left corner of the left-hand side. And this is where you start to see those really visible arcs, those visible sort of distortions and magnifications of background sources. Now, what this talk is going to be mostly about is kind of the opposite regime, which is what we call the weak gravitational lensing regime, which is essentially what's shown in this box here on the right. So you've got images of galaxies which have randomly aligned positions on sky, but because of the gravitational potential, they all have ellipticities that are slightly coherently distorted, and it's that coherent distortion that we're kind of looking for with our weak gravitational lensing signal. So just very, very a little bit of math here to give you an idea of what I'm talking about. So we have essentially the signal that we're trying to measure is the ellipticity of galaxies. And what we can say is that in the weak lensing regime, the ellipticity of a galaxy on sky is essentially its intrinsic ellipticity plus some shear, plus some modification to that intrinsic ellipticity that's caused by the light passage through a gravitational potential. And as you can see, in this regime, this shear signal is very, very small. And so what we tend to do is we get lots of galaxies together and we average the ellipticity of populations of galaxies in order to probe the average shear signal. Now, the reason that we do this is because we can make the assumption that the average intrinsic ellipticity of galaxies is 0. So galaxies don't preferentially have any ellipticity on sky. They don't have any preferential ellipticity or alignment on sky. And as I say down here, that particular assumption can be violated and is one of the things we have to think about a bit later on. But for now, we're just making the approximation that the average ellipticity of a large population of galaxies is essentially a probe of the average shear. And that's the thing that we're interested in for cosmic shear. So here's an image that you have of a galaxy cluster on sky from within KIDS, from within the kilodegree survey that I'm a part of. And what we can do is we can aggregate the average shears of galaxies in the background of this image at various points around this cluster. And what we basically find is that those ellipticities tend to be tangentially aligned, which is the imprint of the gravitational lensing signal. And when you do that, you actually bin galaxies on this two-dimensional plane by their average ellipticity. You can then reconstruct the gravitational potential that created the distortion. And that's essentially what we've done in order to create this thing here, which is a map of the invisible gravitating mass that is present within the cluster. And so this is essentially a dark matter map of this particular cluster, what we call a weak lensing mass map of this particular cluster. Now, what we're doing in cosmic shear is instead of just looking at individual large, massive objects and looking at how their distortions happen, instead what we're interested in is the sum of the distortion effects that happen as light passes through all of the different large-scale structures in the universe. So taking this cartoon, what you can see here is a couple of galaxies in the background, which are here with random ellipticities shown by the blue. And what happens is the light from those two galaxies propagates through the universe and is distorted by different massive line of sight objects like filaments and clusters and large-scale structures. And as these two objects are distorted by the same large-scale structures in parts, different large-scale structures in other parts, and again, the same large-scale structures in the last part, then what is imprinted on the shapes of these galaxies is a coherent distortion. And it's that coherent distortion that we call cosmic shear. And that's the thing that we're interested in probing, because cosmic shear, this coherent distortion of populations of background galaxies, is a direct probe of the matter power spectrum. And that's very useful if you're interested in cosmology, which is what we're interested in weak lensing cosmology. It's in the name. So here's a little bit more just math. Don't get too worried. I'm not going to go through this in any great detail for those of you who haven't seen this before. But sufficient just to say that this is our observable. So this is the average shear that I was talking about before, where we've now turned our G's into gammas for a reason that's not really important at the moment. And what you can see here is this is the average tangential shear, so the average shear going outwards of galaxies. And this is the average shear, the radial shear component, the cross shear as it's called, as a function of angular position on sky. And so this is what we call the shear-shear correlation. And the reason that this is really, really interesting for us as cosmologists is because the shear correlation function is something that we measure on sky, but then can be modeled really, really easily because it directly probes the matter power spectrum. So what we have here is the true underlying matter power spectrum of all matter in the universe. So not luminous matter, not dark matter, just all matter in the universe. And that with two simple, mathematical transformations. So this is just a line of sight integral, and this is what's called a Hankel transform that takes you from your L scale, so your Fourier spectrum, into your real space. And with just those two things, you end up with these shear correlation functions, these psi plus and psi minus values. And so there's a direct link that is completely agnostic to the bias of galaxies. It's completely agnostic to how galaxies actually trace the matter power spectrum in the universe. It's just a direct mapping between what we see on sky and the actual thing that we're interested in probing. So it's a very, very powerful tool with one primary consideration, which is that part of this model here that we have involves this thing, which is this p chi of chi prime. And that's the essentially the redshift distribution of the sources of galaxies that we're interested in. So there is this noisy thing that we have to estimate from the data here, this redshift distribution, that is fundamental to our estimate of the shear correlation function. And that's going to become very important in a couple of slides' time. So how does this work in practice? Well, what we do in practice is we don't just take all of the galaxies on sky, bin them together and look at a single thing. Instead, what we do is we do this thing called tomography, where instead of taking all of the galaxies, we make rough bins along the line of sight. So we bin things into galaxies that are in the foreground, in the intermediate range, and in the high redshift end of our space, of our survey. And what you can see here is 5 such tomographic bins from KIDS. So these are the autocorrelations, the shear correlations within the 5 tomographic bins, 1, 2, 3, 4, and 5, and the various cross correlations that you can see filling out this. And what you have at the top here is the psi plus component that I was talking about. And this is just the other way of combining the tangential shear and the cross shear into the psi minus. And they have very slightly different sensitivities to cosmology, to large scale structures. And so what you can see here in the blue is just my observable. So as again, this is just following the same color scheme from the last slide. Blue here is our observable. Red here is our model, which we've taken from assuming that we have our known redshift distribution. And then we just fit these two things together. And that's how we get our cosmology. That's how we get our shear power spectrum. So it's a very direct probe of this thing that we're interested in. It's very, very useful for us to know. One of the things that we know that we find when we actually do this process is that the shear correlation function is not so much sensitive to individual parameters of, for example, the clustering strength of matter, which is parameterized by this value sigma 8, or necessarily directly to the amount of matter that is present in the universe, but rather there's a degeneracy between the sensitivity of those two parameters, and what cosmic shear is particularly sensitive to is this, what we call the cosmic shear banana, this degeneracy here between sigma 8 and omega m. And so what we generally do in cosmic shear is parameterize away that degeneracy using this formula here into this thing that is called S8. And S8 is just a means of combining these two parameters in such a way that degeneracy is no longer present. So the thing that cosmic shear is sensitive to is movement in this perpendicular direction. And what you can see from this figure is the results that were present in cosmic shear in 2013 from CFHT lens. And you can see that in CFHT lens days, when we had the WMAP7 analyses, CMB analyses, everything was great. Everything was happy in cosmic shear and CMB analyses. Everything agreed, and we were all very, cosmology was very, very easy. Unfortunately, as I'm sure you're all aware, that particular situation did not remain. And so I'm now going to sort of go on and talk about what happened in cosmology in 2020, and I'm going to start by sort of giving you the summary overview of what cosmic shear was like in January, and then how it progressed throughout the course of the year. There are three primary cosmic shear surveys that are active at the moment, and those are the Hypersa PrimeCam survey here, shown with the Subaru telescope, the Dark Energy survey here, and then the Kilodegree survey, which uses the VST VLT survey telescope at Paranal. And I'm going to very briefly talk about the three of them. Now, these three cosmic shear surveys all have particular strengths. The HSC, for example, is unbelievably deep and is extremely sharp, has some of the best seeing of any ground-based imaging, if not the best seeing of any ground-based imaging present. And as a result, the imaging quality and the number of sources, the source density in HSC is unbelievably large. It's very, very large compared to the other two surveys. Conversely, the Dark Energy survey has the widest field of view of all of the cosmic shear surveys, and as a result has an extremely rapid survey capability and is able to do extremely rapid surveys of the entire sky, and therefore has a very wide area, which we'll talk about a bit more. Great. And then last of all, we have the Kilodegree survey, which is the collaboration that I'm working for. Is really in the combination that it has with the Viking survey, an infrared survey that is matched so that they have exactly matching optical and infrared colors and photometry. And also in the fact that the VST was really the first telescope that was ever built specifically with weak lensing in mind. It was designed in such a way that it has an extremely stable and extremely round PSF, achieved primarily by putting the camera from the VST at the Cassegrain focus rather than the prime focus. But as a result, even though it's the smallest telescope involved here, only 2.5 meters in diameter, it really is a powerhouse for weak lensing in terms of systematics control. So this is the status of cosmic shear as of 2020, as of January. And what you can see is essentially the three cosmic shear surveys I was just talking about, where we have kids in the blue and the green for two subsequent analyses that came out of this paper, Hildebrand et al. 2020A. And then you have the DES banana shown here in purple and the HSC banana shown in orange, and the comparison with Planck here. Now, as I said before, we usually don't look at this plane because it tends to smear things out over the banana, and we parameterize this instead in terms of S8. And what you can see here is that the cosmology constraints from weak lensing and from all of the different cosmic shear surveys seem to sit a little bit low, seem to sit a little bit away from Planck. I mean, it's not significant at many sigma for the DES year one analysis, but certainly for the kids analyses, the Planck constraints of S8 seem to sit a little bit higher than our contours would deem terribly comfortable. So this is kind of where we started 2020. We knew that there was still some tension with regards to the CMB. We were hoping that, subsequent analyses might be able to alleviate some of that tension or give us some indications as to why that tension might be there, because there are, systematics explanations that might be relevant, and there are also new physics explanations that might be relevant. But before we sort of establish any new physics or argue for any new physics, we really need to get confidence in our systematics control up and running. And so one of the things that was present, one of the troubling sort of things that was present at the end of 2020 was whether or not we trust the redshift calibration enough for us to be able to make any claims of new physics caused by differences between Planck and kids, for example. And so what you can see here is an example of using the same data set, just with a slightly different redshift calibration sample in the Hildebrand KV 450, so kids Viking 450 square degree analysis. And what you can see is that if you modify or if you change your calibration data set, then you can get a systematic shift in S8 that moves you closer to Planck. And so this is the sort of thing that we worry about. This is the sort of thing that we want to be sure that we are not susceptible to, and was one of the lingering sorts of concerns that we had at the end of 2020. But indeed, the the edge cuts both ways, as they say. So while something like DES would say we don't have any great disagreements with regards to Planck, a reanalysis of DES data done by Judaki et al. At the beginning of this year suggested that should the redshift calibration in DES be done in a different manner, closer to that which is done with kids, then indeed you would find something like you see here, where the DES original N of Z, so the original redshift distribution analysis, gives you these dashed contours. And when you perform a new redshift calibration, more along the lines of what happens in kids, you end up moving away from Planck. So indeed, there are arguments for the redshift calibration procedure leading to less disagreement with Planck or more disagreement with Planck, depending on which survey you look at. So it really isn't an open and shut, oh, it's just the redshifts. This then gets even worse for the disagreement with Planck if you then say we've treated the redshifts in a consistent manner in this particular analysis, Judaki, between DES and kids, and then we combine those two analyses and you end up with a greater than 3 sigma difference between kids and Planck. So it is a significant effect. So that sort of begs the question of how are redshift distributions constructed? So what I'm going to talk about now is how we actually do redshift calibration within kids. And the way in which we do that is through a mechanism called direct calibration. And that direct calibration essentially says I have some distribution of spectroscopic data which have known positions in the distance axis, and I want to then use those known distance objects in order to infer the redshift distribution of the sample of cosmic shear sources, so these background sources, for which I don't have spectroscopy, because there are simply too many of them. To do spectroscopy for 100 million galaxies would be prohibitive, and I'm not sure any TAC would give us that time. And so the way in which we go about this is we have to find some mechanism to map the redshift distribution from spectroscopy onto the redshift distribution from the wide field data here shown as the blue curve, the photometry. And essentially the way in which you do that is by assuming that firstly, there exists some method of mapping observed redshifts in one frame onto wide field galaxies. That's obviously required. And the next is that you have either a representative spectroscopic sample or some method for determining which sources are matched to those spectroscopy in some way, shape, or form. Now, the way in which this was done for previous kids analyses was using this thing called k-nearest neighbor matching, which was suggested first by Lima in 2008 and has been used by kids within 3 different analyses, 2017, 2018, 2020. And what you can see here is just a very, very simple schematic of how this procedure works. So you have some color space here shown as the ith color versus the jth color in my little diagram. And this space is filled both with spectroscopy shown as red and photometric sources shown as the blue. And what you would do is you go to each one of the spectroscopic sources and you ask the question, how many photometric sources exist within the near neighborhood of this particular spectroscopic source? And that number dictates a weight. And that weight is then applied to all of the spectroscopic sources. And that essentially allows you to reweight the redshifts of all of the spectroscopic galaxies in order to create a redshift distribution for the wide field data that is representative of the density of photometric sources in the color space. So this is called the Lima reweighting procedure, or just direct calibration. And there are a couple of concerns that people have with direct calibration. And this was what I was alluding to a bit earlier. So if we take the results from Hildebrandt 2020, and instead of calibrating with the full spectroscopic compilation that we show here, colored by the different surveys that make up that spectroscopic compilation. So you have Z-Cosmos, which is a deep but bright spectroscopic compilation. You have the Deep 2 survey, which is a color selected survey that preferentially observes spectra for sources at redshifts 0.7 and above, and various other compilations. And what happens is if you perform that direct calibration procedure with the full compilation of these spectroscopic catalogs, then you get the purple contours. If you perform it with the same spectroscopic compilation minus Deep 2, then you get the green contours, right? So this is saying that the sensitivity of our value of S8, or our inferred value of S8, appears quite sensitive to the makeup of this reference sample that we have here. And that's a problem, because there's no way of saying or necessarily knowing when that sample is going to be complete enough for you to do your science, right? And so instead, what we wanted to do is try and figure out a way to get around this particular sensitivity. To understand why those sorts of biases are relevant and why that sort of bias happens, this is a simple sort of demonstration. This is our cartoon that we had before, and we had our galaxies placed at the back here. Now, if we were to systematically misinterpret the positions of our two source galaxies as not being at a redshift of wherever this black back line here is at the back, but instead being considerably closer, so systematically nearer to us, then we have the same shear signal. We have the same imprint on the galaxies on sky, but we attribute those shear signals as coming from a smaller volume, essentially, a shorter line of sight. And therefore, we naturally have to interpret that as there being considerably more clustering or matter or both along the line of sight. So this is where that systematic bias comes from. And so what they found at the beginning of this year was that it basically, depending on how you chop up this spectroscopic compilation, you can get up to 0.5 sigma shifts in this direct calibration procedure, and that's not great. And so what we did at the beginning of this year was we devised a new method for calibrating redshift distributions, which involved something called the self-organizing map, which some of you may be familiar. The self-organizing map, in few words, is essentially an unsupervised machine learning method for mapping out a n-dimensional surface in 2 dimensions. So what you can see here is on the left, we have a cartoon that I've pinched from Gary Davidson's work, which shows a 3-dimensional distribution of data of colors you can interpret these as, for example. And what the SOM does is it takes it maps a mesh or a grid to the distribution of those data in the n-dimensional space. Now, in our case, we have a many color space, and we fit this high dimensional grid to the many color space. And what you can see on the right here is an example of a SOM mapped onto a many dimensional color space that I have then just painted by a single color. I've painted it by the R-I color. And you can see that the color of sources within the manifold correlates with position. That is, red things tend to be near red things, blue things tend to be near blue things, white things tend to be near white things. And the reason that's relevant and the reason that's important is because one of the things that we assume when we do redshift calibration is that there exists this thing called the color redshift relation. That is, that things which have similar colors have similar redshifts, have similar distances. And indeed, if you take the same SOM, colored here, or rather a different SOM, but colored in the same way, and you paint it by color on one axis, on one side here, and redshift or true redshift of these cells, then you can see that indeed color correlates with color in the map space, as does redshift. So their low redshift things tend to sit next to low redshift things. High redshift things tend to sit next to high redshift things, with the exception that you can see of this caustic here. And it's worth me saying that these SOMs are what we call toroidal in topology. That is, that they obey Pac-Man rules. So you go out the top, you come in the bottom, you go out the left, you come in the right. And so the edges of these things are essentially connected. The only caustic that you can see is basically this line here that separates the low redshift from the high redshift. And what you can also then do is construct a distance matrix, which basically says, how far away are the grid cells in my SOM here, for example, at the edge of this caustic? And what you can see is that basically at that caustic, the SOM has stretched. And so there is actually somewhat of a discontinuity between these two parts of the map space, but it's still recovered well in the SOM. So the SOM is flexible enough to account for both things that are densely clustered together and widely separated. So that's very useful for us. The reason that this is really, really useful is because the SOM allows us to do redshift calibration, for one, which is just what we needed to do from the k-nearest neighbor method earlier. But it also allows us to directly visualize and directly flag things that aren't represented by the spectroscopy that we're using for our calibration procedure. So what you can see on the left here is a SOM that was used for my SOM cosmology analysis in May of this year. And it's painted on the left by the number density of spectroscopic sources present in our spectroscopic compilation. On the right, it's painted by the photometric data within our cosmic shear sample. And you can see a couple of things. You can see that there are parts of the map where there are many spectra and there are many wide field shear sources. There are parts of the map where there are many spectra, or an overdensity of spectra, but an underdensity of wide field shear sources like this second arrow. And you can see there are parts of the SOM where there are both neither spectra nor wide field photometric sources. And the utility of this map is that we can do this. We can basically say anywhere in this map that there exists a black cell, so where there is no spectroscopy, we fundamentally cannot calibrate a redshift for those wide field photometric sources. And that gives us the ability to flag and remove shear sources that don't have representation in our redshift distributions. And the reason that that is a really important and really relevant thing to do is because we said that before, the apparent bias that we saw in the direct calibration was caused by the fact that we had thrown away deep 2. Right? We'd thrown away a particular part of the redshift space, which also happens to correlate with a particular part of the color space. And so what you can see in this SOM, where I've now colored it by the spec Z so the origin of the spectroscopy within each cell. So these cyan cells that you can see here have spectroscopy purely from deep 2. The yellow cells have spectroscopy purely from Z-Cosmos, and the pink cells have spectroscopy purely from VVDS, and there's the smudgy brown cells that have a mix of the three. White cells are things which have spectra in them that don't fall within any of these 3 surveys. So you saw there were more than just 3 surveys in the previous slide. And the black cells are cells that have no spectra in them whatsoever. Now, the reason this is relevant is because now, if I throw away deep 2, I lose all of my calibration in all of those cyan cells. But I now have a mechanism for saying, yes, I've lost the spectroscopy, but I've also now lost the shear sources that should have been calibrated by deep 2. And what that means is that I can take this biased picture that we had at the end of 2019, I can do exactly the same analysis, but now with this SOM cosmology, this SOM calibration procedure. And if you draw your eye to the top right, top left here, you'll see what's about to happen. We end up removing the systematic bias that you see in S8. So by doing this SOM calibration procedure, we end up with a redshift calibration methodology that is no longer susceptible to pathological misrepresentation of spectroscopy, which is very, very important, as we saw, because that was the main systematic that we were seeing. And indeed, you can now chop up this data set, this calibration data set, however you like, and the marginal constraints on S8 basically don't change. You see this green contour here, the marginal constraint seems to shift a little bit to lower S8, but what you can see from the 2D posterior here is that that's basically driven by an extension of the posterior to smaller S8 values. And the reason for that is because, like I said, when we throw away deep 2, we have to throw away all of these blue cells and every single photometric source, cosmic shear source that sits within them. And so when you do that analysis, you actually lose about 40% of the data set. And so that's a considerable loss in statistical power that causes a broadening of the contours, and that's why you see this extension here. So it's not systematic. That's the important thing. We then also found some interesting things at the same time, some interesting sort of correlations between different parameters in this analysis. So we found that part of the difference that you can see between for example, the KV450 calibration with the K nearest neighbor method, which is shown here in purple, versus the SOM method, which is shown here in orange, that difference can be almost entirely attributed to this correlation that you can see here. This is the S8 correlated with the intrinsic alignment amplitude. And you'll remember that I said at the beginning that we can assume that the average ellipticity of galaxies is 0. And that is wrong. you can't make that assumption. The reason you can't make that assumption is because of two effects called the intrinsic alignment, the galaxy intrinsic alignment, and the galaxy intrinsic alignments. And I won't go through what they are for now, but I'll suffice it to say that when you perform the redshift calibration in a robust way, you end up finding out that the very small residual differences that you have in S8 can basically be attributed to how you model IA, how you model intrinsic alignments, and how well you constrain the intrinsic alignments of galaxies. So this is kind of where we start at April of 2020. And I see those of you looking at your watches saying we're now at 20 minutes to the hour, and Angus is only up to April. So I'll do my best to speed up a little bit. The unfortunate circumstance, or the unfortunate situation that we find ourselves in, was that in April of 2020, we hadn't resolved any of the problems or any of the tensions with regards to Planck. In fact, we had resoundingly, one would argue, said that the possible argument that the redshifts from kids were being underestimated and that was the systematic that we saw have been disproven, because we no longer see that systematic. We no longer see the contours being pushed to higher values closer to Planck. And so instead, we're now at a situation where there is one less thing that we can attribute to the difference between Planck and kids. And so that then brings us to the next development. That was something that happened in the end of July of 2020, which was the release of the KIDS 1000 cosmic shear analyses. So this is a map of the footprint of the KIDS 1000 survey, which is a mass map. So you'll remember that I showed you that map of the mass map of a single cluster at the beginning. This is now the mass map of the entire survey of kids, and very artistically done, I should say, for a couple, mostly because firstly, the two halves of kids do not sit next to one another on sky, or rather more importantly, neither of them go through the center of the Milky Way, which would obviously have some implications for the sensitivity of the survey, to say the least. The survey release for the KIDS 1000 analysis was sort of summarized by these sort of 6 primary papers that were released over the course of the last few months. I won't go through all of them, obviously, because I don't have nearly enough time, but there are a number of videos online of presentations about this analysis if you find what I'm about to show you interesting and would like to know more. So the first thing that happened, or one of the first developments that I'm going to focus on for the KIDS 1000 analysis, was moving beyond these purely shear correlation functions. So you remember that I said that we have this thing called the shear correlation function, and it's a direct mapping of the matter density parameter. One of the things that I kind of ignored over that entire discussion was this transform that you have to do to go from the real angular scales here to the L scales, the Fourier transform here. And the reason that's sort of a naughty thing to ignore is because one of the things that happens is we're essentially trying to map discrete datum in this L space, in this Fourier space, because that's where our sensitivity, that's where our cosmology lies. But we're doing it with this angular parameter theta, this angular physical scale thing. And what happens in the course of that transformation is you essentially smear out the Fourier information over a huge baseline. And so what you're seeing here on the right is the psi plus and psi minus curves. So essentially, before doing this integration here, what do these distributions, what do these functions actually look like for a couple of values of theta? And this is what they look like. And you can see that there is information coming from all like wildly different L scales. And this is important for a couple of reasons. And probably the main reason that it's important is because there are significant systematics that correlate with our estimate of the matter density parameter to do with, for example, baryon feedback, that kick in at very particular values of L. And that's something that we'll look at in a second. So one of the main developments that we made in KIDS 1000 was to extend our analysis away from just having the shear 2-point correlation function to having these additional metrics, these additional 2-point statistics, which are the Casades, the complete orthogonal set of E and B integrals, which is essentially a combination of the different shear real space shear angular correlation functions that are combined using a weighting that essentially localizes exclusively E modes, which are the tangential modes that are this tangential component here, versus B modes, which are the things that create the cross shear component. And those are things that can't be created by weak lensing, and so essentially is a means of determining systematics. And so the first Casades really help localize the shear correlation function down to a smaller L scale. But we can then take that even further by saying, instead of actually going through this whole loop, we can construct these things called band powers, which are essentially designed to be top hat functions in this L space, in this Fourier space. Now, they're not exactly top hat functions, as you can see here. And the reason they're not exactly top hat functions is essentially because these integrals here go from 0 to infinity. And we don't have infinite angular scales in our survey, which means that we have to truncate these integrals at some point, and that gives you some of this noise and some of this up and requires some thought. So this is detailed quite at length in Asghari et al. and in Joshimi et al. I'm going to focus on the band powers for a second because I think that they're really interesting. And essentially what is most important is you can see, so these are the band powers that I just showed you in terms of L. If we then take these band powers and we look at what they look like in terms of the physical scale, so the angular scales, that's what you can see here. So these are the different band powers, the first and the eighth, for example, if you're just counting along. And you can see that they are, wild combinations of different angular scales in order to create these top hat functions in Fourier space. But when you make these distributions and you then reweight all of your theta scales by what is essentially this blue function here or this orange function here, you end up getting these distributions that are essentially top hats in Fourier space. And that's really useful because one of the things that I'm showing at the top here is that the angular scales here, the Fourier transform of the angular scale here maps out to particular physical scales in terms of as a function of redshift. So if I go to, for example, an L of 10 to the 3, then at low redshift, I'm essentially looking at K scales of between 1 and 0.3 H per megaparsec. And the reason that this is relevant is because I was saying to you that at a particular point in L is where baryon feedback kicks in, and it's actually at a particular point in K, but because these two things are somewhat related to one another, then you can use these band powers are essentially considerably less sensitive to, for example, AGN feedback, baryon feedback, which kicks into the power spectrum at Ks of between 0.1 and 1. And so if we are essentially at K scales of greater than 0.1, so if we're out here, then we're not sensitive to baryon feedback, which is great. We can then actually just show this using the analysis. So what we did in KIDS 1000 was we did an analysis of the actual data set, assuming that the universe contained no baryons. Naturally, that's an untenable position because, we are here. But what is interesting or what is relevant is that when you do this analysis, assuming that the universe has no baryons versus assuming that it has some fiducial setup where baryons exist and have a particular feedback and you see that the band powers basically don't change in their results of S8. So this is the S8 or sigma 8 in this case. What the difference is not terribly important right now. Between the no baryons case and the fiducial setup, and it's expressed as a sigma. And what you can see is that if you're using band powers, you're essentially, or you're much less sensitive to assuming that the universe has no baryons in terms of your constraints on S8 than you are if you use 2-point correlation functions, where that assumption gives you a greater than 1 sigma bias in your S8 value. So the use of band powers really dramatically reduces our sensitivity to that parameter. The last thing that I want to talk about is the statistical phenomenon that we discovered, which is probably not entirely surprising to the statisticians in the audience, but was relevant and interesting to us, which was that when we discovered that we had sufficient power, sufficient statistical and systematics constraints to be able to be pulling our constraints on S8 down to the sorts of levels that we had for Kids 1000, one of the things we noticed in our simulations was that we were getting posterior constraints, shown here as the marginal constraints in omega m and sigma 8, that didn't overlap in the marginal confidence interval with the truth, the underlying truth, and indeed the maximum of the posterior in n dimensions. And what we discovered, or what we rediscovered if you're a statistician, was that essentially this is to do with the way in which pathological posteriors behave when you do marginalization. So here I've created, or rather Tillman Troster has created, a pathological posterior which follows the expression you can see here at the bottom. And this is designed to be pathological because the maximum of this distribution is at 0, 0. Okay, so the truth that you're looking for is at 0, 0. And if you do a conventional posterior marginalization, then what you find is that your marginal constraints, which are generally what are quoted in the literature, give you values that are catastrophically away from the truth in the noiseless regime. And this is basically just due to the fact that you have a complex posterior space. You have a set of priors and a set of data, and this is driven by the complexity of the posterior space and where the samples sit in n dimensions. And so instead of doing this conventional marginalization, what you can do is this thing called the joint highest posterior density, the projected joint highest posterior density analysis, PJHPD. And what that essentially does is, instead of creating a confidence interval or a marginal constraint based off the peak of the marginal and then integrating outwards as is done in traditional confidence intervals, or quantile confidence intervals as they're called in statistics, instead what you do is you essentially create that integration outwards from the peak of the posterior in n dimensions. And that's what this PJHPD does. And you can do this for all of our statistical analyses, all of our cosmological constraints. And so now in Kids 1000, we have this improved posterior inference where we quote both the typical marginal HPD, which is what has been quoted in the literature, for the last 10 years, and also the posterior joint HPD, which consistently recovers the underlying truth, which cannot be said for the marginal version. So this is kind of where we ended up. This is where we sat at the end of 2020. I was very much hoping to have a DES addition to this slide, but unfortunately it looks like there's a holding out for everybody to return from their Christmas holidays to make a big splash at the beginning of 2021. And we're very, very excited to see the results from DES's next release. So the DES Year 3 analysis is going to be, really something. What you can see is that with the Kids 1000 analyses and cosmic shear, our constraints over cosmic shear increased. We made an improvement in the uncertainties of almost a factor of 2, but unfortunately, because of the movement of the center of that posterior distribution, the tension with Planck is almost exactly the same. So very frustratingly, with an increase in statistical power, we've not made any significant inroads into telling whether or not the difference with regards to Planck is real or is a noise fluctuation as yet. But that brings me to the last thing that I'm going to talk about, which is the last slide, which is just what's coming next. And that is essentially to say that the next thing is going to be DES Year 3, and we're all very, very excited to see what DES comes out with. In HSC, the HSC survey has only used 10% of their data to date. The next data release is going to be another 20% of their data, and they're already at competitive levels with only 10% of their data. So we're all extremely excited to see what comes out of HSC in 2021. And the final thing is the Kids Legacy analysis, which is going to be the release and the cosmological analysis of the final additional 30% of kids which fell outside of the Kids 1000 footprint, but also includes double depth imaging in one of the photometric bands that's particularly relevant, the I band for the high redshift calibration, and an additional 6th tomographic bin that we're going to be able to calibrate at high redshift. And the really interesting thing about that is that 6th tomographic bin, just based on our initial Fisher forecasts, is going to be to add sufficient statistical power to our, or equivalent statistical power to our analysis, the same amount of improvement in statistical power as doubling the area of kids. So this sixth tomographic bin really will give us another route to in statistical power. So it's a really exciting time in cosmic shear, and it's going to be really interesting. The big question is whether or not all of these surveys can keep a handle on their systematics down to the level that's going to be required in order to actually utilize these increases in statistical power. And beyond those, whether something like, you know, the Euclid survey or the Vera Rubin Observatory Legacy Survey of Space and Time, LSST, is also going to be able to do that. So those are sort of the upcoming cosmological analyses and what we have to look forward to. And I'll stop there. Sorry that I went a bit long.
Thanks a lot, Angus. And let's thank him by using the applause reaction. I find that unmuting mics and having everyone clap doesn't always work the best, but thank you, Angus.
Thank you.
And if you have any questions you'd like to ask now, feel free to use the chat or raise your hand in the participant list. I see a question from Bryce.
Yeah, what is the main factor that determines how many tomographic bins you use? Because you're really excited about the 6th bin, but why did you use 5 in the first place?
Yeah, that's a good question. The 5 tomographic bins, well, I mean, indeed, initially with kids, it was 4 tomographic bins. The 4 tomographic bins were determined because of the photometric redshift baseline that you can make with U, G, R, and I bands. So at a redshift of 0.9, the 4,000 angstrom break enters the I band, and that essentially means that you lose photometric redshift capability or significant sensitivity to photometric redshift capability with only UGRI. We then added the Viking data, ZYJHK, in the kids Viking 450 analysis, and that enabled us to use this 5th tomographic bin, which we defined as being between 0.9 and 1.2. The motivation of 0.9 to 1.2 was twofold. The first of which was that the redshift, so the redshift calibration requires us to use simulations to verify calibration methodology, and currently redshift simulations out to, well, we were using the MICE2 data set for our simulations, and that simulation data set ends at 1.4. We didn't feel very comfortable butting right up against 1.4. But the main reason was because the modeling of SEDs and the modeling of sources for colors in these simulations beyond redshift 1.2 is a bit sketchy already. And that's basically just because the majority of these surveys tend to use, or the simulations tend to use, SDSS, then extrapolated out to high redshift. And it turns out that the redshift 1.4 universe doesn't look a lot like SDSS. Probably not surprising, really.
Any other questions while we're here?
I will qualify on that particular statement that setup, that situation hasn't evolved into a great deal. So the simulations at high redshift are still somewhat uncertain, and we are one of the main things that is happening for Kids Legacy is the upgrading of our simulations to use the Euclid flagship, which firstly extends to much higher redshift. And we hope will therefore allow us to get a robust calibration of the 6th bin. And that's primarily what motivated these Fisher forecasts and things. We basically wanted to know how well we had to calibrate the 6th bin in order to get significant benefits. And so, yeah, it's very much an open question, but we're all very, very excited. From the preliminary looks at those Fisher forecasts, it really is going to be a game changer for kids.
I guess I've got maybe more of a statistical analysis question, but it looks like the work that you did with the self-organizing maps replacing KNN seemed to allow you to really take care of, the redshift distribution of the different spectroscopic surveys you had. My question was, is there a reason that you picked self-organizing maps over other things like TSNE that map to 2D?
Yeah, the answer is no. So I mean, I picked SOMS predominantly because I was sitting in a Euclid consortium meeting where Peter Kapak and Dan Masters were talking about C3R2, and I saw SOMS for the first time, and I thought, wow, that's really cool. And then I discovered that statisticians had been using them for over 40 years, and was quite humbled. And so there is no great reason. It is an extremely versatile tool in terms of visualization, but that's also true of other machine learning methods. It's essentially just a mechanism for discretizing and associating sources in a complex space. You don't necessarily have to use SOMS. You could use whatever you like, and there may well be better tools out there. But for the accuracy required by kids, this appears to be sufficient for now, and is much better for just a number of reasons than what we had done previously with the nearest neighbor.
Yeah, it looks like it's working really well. So, why break it, right?
Yeah, it really was a vindication of all of the work that we put in. It was looking very sketchy for a while there. And the part of the reason for that is because with the simulations that we had, we were able to generate, let me try and skip through here. That's a really great picture, but it's not what I wanted to show you. There we go. So no, that's not what I want to show either. So one of the things that we found was that the complexity of our simulations allowed us to diagnose some systematic biases that we had absolutely no idea would be present in our data set. And the main one of those is that when you do tomographic binning, when you bin wide field sources based on their photometric redshift, because photometric redshift correlates with true redshift, you end up applying a differential redshift dependent selection bias to individual color cells. And that is to say that if you take a spectroscopic compilation without any tomographic binning, and you calculate the N of Z for every tomographically binned photometric source in a single cell, so what you can see here on the right, then the redshift distribution that you get out will be wrong. And the reason it will be wrong is because the tomographic binning of the wide field data has imparted a really redshift dependent selection function on every cell. And so that's what you can see on the right. What I've done here is I've colored the SOM by the mean redshift of all photometric sources minus the photometric sources that just reside in tomographic bin 1. And you can see that at low redshift, which is basically what this cloud is down here, everything's fine. But then there is a high redshift tail, and that high redshift tail has been asymmetrically sampled by the tomographic binning, and that it leads to catastrophic biases in the recovered N of Z. And so when we first started doing this, especially for the highest tomographic bins, we were getting, biases in redshift distributions that were 10 times what they were with the K nearest neighbor, and we had no idea why until we discovered this particular effect, and it necessitated a complete change in how we did the binning of the spectroscopic and photometric sources and how they were combined and things like that. And this is absolutely relevant for people doing tomographic binning, so for LSST and things like that. This is one of the things that we were discussing quite at length during the LSST tomographic challenge.
All right, last chance for any live questions here. All right, if that's all for questions, let's thank Angus again.
Thank you all for your very nice comments. in the
And I'll
chat.
also, I'll also remind everyone that we'll have, so tomorrow morning, because of time zones, Angus will be available for meetings between, I'm making sure I'm getting the time zones right, 9 a.m. and 11 a.m. Pacific. Yes, those are the right time zones. So we'll send that Google Doc around again if you'd like to sign up for a meeting slot. But thanks again for presenting, Angus, and I guess some of us will talk to you tomorrow.
Great. Very much looking forward to it. And thank you again for having me.
See you later.